All right. So we are recording at the moment. Let's get started and let's share the whiteboard. And over here, again, I'm going to do an example of continuity problem. All right, and that's going to be question number 45 of section 1.8, which is our section on continuity. And then over here, we have a given function, and the function has a formula f of x equal to cx squared plus 2x if x less than 2 and x cubed minus cx if x is greater than or equal to 2. So the question is to find a constant c such that this function is continuous everywhere. So find c such that f of x is continuous everywhere. All right, so we want this to be continuous everywhere. That means that when we look at the graph of a function, folks, we should not see jumps in the graph. So we should see everything, all the branches, connecting with each other. So we don't have any sort of jumps in the graph. And I'm going to show you how to do this problem mathematically, by just looking at the points of continuity and such. But for the moment, let's take a look at Desmos. And I'm going to turn on Desmos here in a second. So Desmos, there we go. So Desmos, oh, you don't see Desmos. So 1 second, folks. So let's do another share. So I am going to share Desmos. There we go. You should be able to see. All right, and I'll do a graphing calculator, and I'm going to plot that particular function. So let's see what the function was, folks. Need to get here closer to the other screen here. F of x equals, and in the book they tell us if x is less than 2, here's a formula. So I'm going to do, again, this is a piecewise defined function, folks. Yeah. Remember, we put everything between these curly braces, and then we're going to write if x is less than 2, colon, and we're going to do cx squared plus 2x. All right, and it's already telling us that we should add a slider c, and I'll do the slider, but after I write the second part of a formula, which is when x is greater than or equal to 2, colon, x cubed minus c, minus cx. There we go. So we got the function, and I'm going to add a slider c, and I'll say, c between -10 and 10. Maybe we should actually work a little bit on these sliders. So let's say this slider, let's make it between negative 2 and 2 or something like that. All right, -2 and 2, and we'll have a step of 0.1. All right, so that doesn't do much, it just changes the slider slightly. But the thing is, what is our function? So let's see. Okay, so I'm gonna zoom out. Oh, okay, well, there we go. So here's what happens with our function. As c slides, there is a break obviously here, so there's a problem over here. What point is this? Oh, that's 2 right here. Okay, so there's a problem at 2. These branches don't connect at 2. So obviously not continuous. And we want to figure out, maybe from a picture, what's happening, when do we actually have a chance of getting a continuous function. So let's see. Oh, look at that. They almost, oh, there we go. So they connect at some point. You can see that. it exists somewhere there. But generally, if you look at this picture carefully here, folks, they don't connect. So there is only one value here, not that one. A little more this way. Let's see. Oh, there we go. Almost. So let's move this a little bit here. No, 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 no. Oh, okay. Oh, right here, about right here. So between zero point 0.6 and zero point 0.7 somewhere. All right. So it seems like they will connect when C is between zero point 0.6 and zero point 0.7. And we want to figure out exactly what is this C where the two branches actually connect. So that's the problem that we're looking at, folks. This is a continuity problem. And I'm gonna exit out of this thing here. So if you want at home, you can play again. You can play this game that I'm playing here. So let's see, run up and down and see what the graph is doing. I'm gonna stop sharing that screen. And I am going to move on to another screen, back to the whiteboard, and we're gonna solve that rigorously. So we saw that the problem for this function was at where x is equal to 2, right above there. So there was a problem there, and it's not surprising because outside 2, if you're to the left of 2, you have that continuous parabola. And if you were to the right of 2, you had this cubic equation, the degree 3 polynomial, right? So these are fine actually, and really the problem is at 2. So the problem here really reduces to, and let me just make sure that you all see. Let me just double check. Oops, clicked on the wrong button. So you all see the whiteboard here. Oh, there we go. So the problem is to make the function continuous at x equals 2. Because besides x equals, so one second, let me move this screen out of my way here. There's always a small screen that bothers me here when I write. So the function continuous at x equals 2. In other words, we want the two branches. We saw that there were two branches, right? So we want the two branches connected above x equals 2. We want the connected there. And what do we do to connect them? So basically, what we do, folks, we're gonna say we want the limit, and this is a key part here. So we want the limit as x approaches 2 from the left side of f of x. We want that to be equal to the limit as x approaches 2 from the right side. So we're going to put a plus in the exponent here of f of x. And we want that to be equal to the value at 2, which is f of 2. So we want these three things to be equal. That's the definition of continuity. Now let's see. What is the limit as x approaches 2 from the left side of f of x? Well, on the left of 2, f is given by this formula that I'm circling here. So the limit as x approaches 2 can be calculated by substitution in this particular formula. So substitution, that means by setting x equal to 2 in this formula. So we're going to get c times 4 plus 2 times 2, right? Because x is equal to 2. All right, we want that to be equal to. And obviously, this can be simplified a little bit, but don't worry about that at the moment. We want that to be equal to the limit as x approaches 2 plus. That means from the right side. Well, if I come from the right side, then I'm going to be here. I'm going to use this formula here, which is the one from the right? And I substitute x equals 2, the exact same thing that I did earlier. And I'll have 2 cubed minus c times 2. And I want that to be equal to the value at 2. So the value at 2, you just substitute 2 in this formula because at 2, the function is given by this. So that's going to be, again, 2 cubed minus c times 2. So these two are redundant. We can just keep one of them. I'm just gonna, I'm just gonna keep this one here, and the equation will be 4c plus 4. I'm gonna write underneath here equals, and from here we get 8 minus 2c. So this really is, excuse me. So we move a c around. So 6c is equal to 8 minus 4. That would be 4. And then you can see that c is equal to 2/3 or 0.666 da da da. All right, so so what you have here, folks, this c that we get here is really, that's why it turned out on the screen there, it turned out to be between 0.6 and 0.7, because it really is 0.666. So it's a number of 6 is there, and that is the answer to our problem. Now, does anybody have any questions for me here, folks? All right. So okay. So if there are no questions, just keep in mind how this is the answer to the problem, folks. Keep in mind how this problem is addressed. There's a similar question, number 46, and I will put some of these for you in the practice problems. And there's a few other questions that can be done from here, but I'm not going to worry much about those because I want you to do those at home first before we do any further questions. So please do review this section along with the ones that we covered up to this point, and that's going to be essentially the material for your exam that's coming up this Friday. Also for Friday, we are going to discuss a little bit of derivatives here. So there's going to be questions with derivatives on this test. But we haven't done any of that, so let's move on and let's do those next. So my next goal here is to discuss derivatives, and okay, received a notification that Amanda joined my my class. All right, so sorry about that. There's a bunch of things popping up on my screen. I have to check them and close them. All right, so 2.1 derivatives and rates of change. All right, derivatives and rates of change. Okay, excellent. So this is what we are going to deal with in the for the rest of the semester. By the way, folks, what we did here, we finished up the entire thing, the entire section on limits and such. And this is the one of the so calculus has really three important parts, at least what we learned here. So there's one part on limits, so that's number one. There's number two. There's a part on derivatives. This is what we start today, and then finally number three. There's a part on integrals. Now these are the key. This is the core of calculus. Now, if you move on and you discuss calculus in several variables, or calculus 2. For example, there's other parts. There's a part of on series, which is a combination of, if you want, limits, derivatives, and integrals all together. So it's in some way a summary of what we do here. And then there's a multi-dimensional calculus, which is again limits, derivatives, and integrals, but that will be in several dimensions. So that's a bit of a slight difference between the two of the three of them, but for the time being, let's focus on derivatives on our end here. So the problem of the tangent. So it's the usual problem that we discussed this earlier in the semester when I gave you an example as a limit, because you can think of that as a limit. You have a function, and it doesn't have to be necessarily a parabola. It could be any function, and you take a point here, and that, let's say that corresponds to a point, I don't know, A on the x-axis, or a point, let's get a concrete number here. Instead of A, let's put something like 2 or something like that. And then you, of course, you have a point 2 comma f of 2 on the graph here, right? This is the graph of a function y equals f of x. And you would like to draw a tangent line. So to draw a tangent line would be easy to simply kind of define, well, it's a line that intersects the graph with only one point. But the reality is that that's not that simple. And we're going to proceed like I explained you with Newton's idea was to pick another point on the graph, connect those two, something like that. Make a point a comma, I'm sorry, not a, let's say x over here. Put a point x comma f of x over here, and let this point slide toward the other one on the graph. And that's the case when this line, this is called the secant line, will slide toward the other one. So let me redo that exercise in case you've forgotten. So the 2 points on this line, this is the secant line, right? This is secant line. And the slope of this line is going to be, and I'm going to write here, the slope is y2 minus y1 divided by x2 minus x1. So that in this case is going to be f of x minus f of 2 divided by x minus 2. So that is the slope of the secant line. Now, if you want the tangent line slope, so this is slope of secant line. The slope of a tangent line is the following, is the limit as x approaches 2 of f of x minus f of 2 divided by x minus 2. So why would I take the limit again? That's because when x approaches 2, again, this point here, folks, slides on the graph, slides towards the other one on the graph, and then the tangent line, is lining up with the secant line is lining up with the tangent line at that point. I explained you that was the key idea, the genius of Newton. When he found that there was so that pretty much is one of the things that is at the base of calculus. This idea of constructing the tangent as a limit. Now, this was a brilliant idea, and of course, one would attempt to calculate limits like that and slopes of tangent lines and things like that. Would attempt to calculate that for every point on the graph, but that would be a bit of a cumbersome process. You know that even when we did the parabola x squared minus whatever y equals x squared, I think was the formula that we used. It required a little bit of calculation. It was a slope, a limit, and stuff like that. The limit needed to be simplified a little bit before we could actually calculate the limit. We will do a similar calculation today, but before we do that, let me just point out that this number here, this limit that we calculate here, is called the derivative of f at 2, and it's denoted like that with a prime sign here. So as an exponent to the function f. So we're going to define definition. The derivative of the function f at x equals 2 is the limit, and I'm going to say here exactly the definition that I wrote up there, limit as x approaches 2 of f of x minus f of 2 divided by x minus 2. And that is denoted like that, f prime of 2. All right, so with this definition, you say, oh, okay, but didn't we say that this definition is the slope of a tangent line? Yes. So that is true, and we're gonna make a comment here, but this is a very important comment here, folks. Gonna comment. Okay. All right. Sorry about that. Why did there we go. Let's say, you know what, instead of comment, because comment might be a little, it's a small thing. So let's say, let's say also part of the definition. So let's say here, so you can take this definition as your definition of a derivative, or equivalently, the derivative at x equals 2 is the slope of a tangent line to the graph at the point 2 comma f of 2. Remember, we looked at that, so that was the derivative. All right, so this is the second version of a definition. So either of these is good. In practice, we're going to use this one. That's why I put this one first, because we're gonna calculate derivatives of that. But this is also very important. And finally, there is a third one. And I want to point this out, so I'm going to redo the picture here. So let's say we have something like this. And you see that when you, of course, you have this slope of a tangent line and the secant line here. But when you write this quotient f of x minus f of 2 divided by x minus 2, this is the point x comma f of x, and this was over here the point 2 comma f of 2. When you write this thing here, what you'll do, you will notice that this is, the rate of change of y, of the y coordinate. So the difference between f of x and f of 2 is y2 minus y1, if you remember, and divided by. So let me actually not write here. So let me 1 second, folks. So let's get rid of that from here, and let's write underneath here so we have more room. So again, f of x minus f of 2 divided by x minus 2. Let's say this. So let's say those of you who have taken physics or are taking some physics, you will write it there as delta y over delta x. And in math or in chemistry, folks, so in math we like to say the difference of y's divided by the difference of x's. Or some other people might say the y differential divided by the x differential. And this thing that we divide here as the y differential divided by the x differential is actually going to be called rate of change of a function x of a function f of x, f is a function of x, or you could simply say of y. So some people say that, and it's in chemistry it's important because this rate of change is let's say F represents the amount of heat produced by a chemical reaction happening, and T is the X is the time of that reaction, and as F changes, as the amount of heat changes, it's important to find the differential. So let's say the initial amount was this much, and then while the reaction kept going on, you have different other amounts of heat, and it's nice to know the differential and the rate of change. How fast, how much does this amount of heat change? as you move on from the starting point of the reaction. So that's pretty much what this is used for in chemistry or physics, for example. So this is a situation that you will encounter in practice, and I want you to be familiar with this type of terminology. Again, a number of people will not call derivatives, but rather they will say the rate of change in practice. So just be aware that there's going to be people who will say that. And in fact, we are going to do some applications of derivatives, and we are going to use the notion of rate of change. So to summarize the point of this lesson here, there are three equivalent definitions of derivatives at 2. And I'm going to point them out. So first of all, the notation is this: f prime of 2 is limit as x approaches 2 of f of x minus f of 2 divided by x minus 2. All right. The second one is the slope of a tangent line at 2. And the third one is the rate. It's called the rate of change at 2. Of f at x equals 2. Now that really means, folks, so the terminology is a bit vague, and in your book you will find the rate of change used interchangeably with something that would be the correct thing, will be the instantaneous rate of change. So that will be the correct terminology. But a lot of people drop this instantaneous rate of change, and they'll just say rate of change at 2 versus rate of change, the limit of rates of change, around 2. So that is the definition of f prime of a derivative. And I want everybody to kind of take, some time to digest this definition and, see how that is applied in practice. And I'm going to do some calculations. So again, because of the nature of this recording, again, I told you that nobody really likes to see, dead timings during the recording. So I'm going to keep moving. But what I want you to do at home is to, take 5-10 minutes or so, or maybe more, and kind of digest this definition, break it up, and understand everything that we did here, because this is going to be really key for us as we move on to some other things. And we develop notions related to the rate of change. So right now I'm going to do some examples, and these examples are the following. So there will be in the next section we will do a bunch of formulas, but for the time being we can do some very simple ones. So let's say, folks, this is a function. This is the x coordinate, y coordinate there. And let's say we have a function y equals 3. So if y is equal to 3, what sort of line is this going to be? This is going to be a line, right? A constant line. Is it going to be horizontal or vertical? I'm trying to see. Let's see. So tell me in the chat, folks, is this going to be horizontal or vertical? What is this going to be? Or you could say f of x equals 3 equivalently. So what sort of function is this? So just say in the chat, folks. Just want to make sure that everybody is with me here. All right, so wait for you to write me in the chat. Okay, so there's a couple of All right, it's a horizontal. Very good, very good. So it's a horizontal line. Yeah, excellent, excellent. So folks, indeed, this horizontal line is gonna be the following. So it's gonna be it's gonna look like this, right? At 3 here. And it's very easy to say what the slope of a tangent line is. There's no doubt in anybody's mind, I guess, that if we want a secant line, if you want a secant line on this picture here, what you have to pick any point you want here. Let's say x equals I don't know. Let's say x equals 1, right? Well, actually, unfortunately, this is not well. Hang on a second. So I'm going to do some other number. Let's say maybe 4. How about that? Just to kind of keep some proportions here properly. So let's say x equals 4. What is going to happen with a tangent line? A tangent line is going to connect this point, which is 4 comma 3, to this other point here, which is I don't know, x comma 3. Right? So it's going to be that, and that is pretty much going to take care of a problem, because when you calculate the slope of or that rate of change, if you want, of the secant line, so the secant line will have a slope of 3 minus 3 divided by 4 by x minus 4, which is going to be 0, which you already knew because this line has constant slope 0, right? It's a horizontal line. So the slope of 0, when you take a limit of zeros at any value, whether x equals 4 in particular, the slope will be 0. So the slope of the tangent line here will be 0, will be the same. The tangent line will be the same as the line you started with the graph. So the slope of a tangent line at 4 comma 3 is equal to 0. All right, so the slope of the tangent line is 0, which would tell us that the derivative is, and I say here, 0. The derivative is going to be 0, folks. Oops, circle that thing again. All right, it looks like it's a bunch of O's there. There we go. So the derivative is 0, folks. All right, so the derivative is 0 for this function for f of x equals 3 or y equals 3 or something like that. Okay, now I hope this makes sense. Let's do another example. Let's say f of x equals, I don't know, 3x. So let's graph this particular function. I'm going to move on to the next page here. Example, let's write again. I have to copy that again. You don't have to write again, folks. F of x equals 3x. The graph of this function looks like, hang on a second, you know what? I have these straight lines, so let me take advantage of that. There we go, there's one of them. And there's another one. And x equals 3 would be something like this, maybe. Goes through 0, right? There we go. All right, so let's say that's x equals 3. F of x equals 3x. I meant f of x equals 3x. It's a line, right, folks? Going through the origin. And again, let's say we want to calculate the limit x at some point here. Let's say some point. I don't know what point should this be. Let's choose 2, for example. And how do we calculate the tangent line at not the limit, the tangent line, folks? How do you calculate the slope of a tangent line at 2? Well, we can look kind of like we did in the previous example. And we can see visually, so see the graphical description is very important here. Visually, we can actually see that this is a line and the tangent line is the line itself. So all I have to say is the slope of tangent line is the same as the slope of this line, and that is equal to 3. So it's that simple. You could say that. So that would be a legit way of going about finding the slope of a tangent line or the derivative. But you could also argue like we did in the previous problem. So let's take another point here. Let's say this point would be, let's say x is here. So x comma, I don't know if, oops, 3. 1 second, folks. It's kind of erasing what I wrote here. So let's say this is x comma 3x, right? Because that's what it is, the formula here. And the slope this is the secant line, right? So the slope can be calculated certainly as saying 3x minus this point here is 2 comma 3 times 2, which is 6. 3x minus 6 divided by x minus 2. So the difference of y is divided by the difference of x. You can calculate this, and you can factor 3 times x minus 2 divided by x minus 2, cancel out the x minus 2, and you'll see that you end up with 3. So the slope of the secant line is always 3. As we go to the limit, as x approaches 2, we're just calculating the limit. So, or you could say the limit as x approaches 2 of the constant 3, which is equal to 3 again. So either way, whatever you do with rates of change or simply observations, you can say that the derivative of this function at any point for that matter is always 3. So the slope of a tangent line is always 3. That's what we're saying here. So this is the example with f of x equals 3x. Now I'm going to give you one more example, and it's something that we've already sort of touched upon here, just to have a complete set of examples here, folks. So let's say we do f of x equals to 2x squared. All right. So if we want to calculate, find the derivative at x equals, let's say x equals 1, for example. Yes, please. So there's a question on the screen. Sorry about that, folks. No, that Ali is asking if an answer like 3/1 be wrong. No, sir, no, it's not wrong, but I would prefer not to write 3/1 because you always want to write in a simplified form. So it's not wrong. I will understand. I will not take off points, but I would prefer that you write just 3. So try to simplify. Don't carry on that denominator. There's no point to carry that on. Yep. All right. Okay. So let's do the derivative at x equals 1. Now we won't have that much luck that we had in the previous problems. So let me share with you here. Let's go back and let's share again the screen with Desmos. All right, so let me see if I actually, let me see that we're doing okay here. Yep, there we go. So I'm going to wipe out this function. I'm going to do that one that I just put there, f of x. What is f of x? Oops, not that. F of x equals 2x squared. And we said we want to calculate the derivative at 1. So which means we want to calculate a limit of the following thing. So we want to calculate the limit of the slope of a tangent line, right? So let's pick a point here. Let's say a point here, and let's see how the slope of a tangent line goes. And for that matter, so what I'm going to do here, folks, I'm going to show you the equation of a secant line. First of all, the equation of a secant line will be something along the following lines. So let's say we wanna pick a point. You know what? Let's do that first. Let's say we want to pick a point a comma f of a, right, on the graph. All right, and that point, since I didn't specify a, the function, the software is confused. It says, do you want a slider? Yes, I want a slider, actually. And we go from -10 to 10. No, I want to go from -1 to 1. That's good enough for me. And as you move this thing, you can see that my point, you know what, let's zoom in a little bit here. My point here just goes, you know, from -1 to 1. There we go. So that's my point on the graph. And I don't want just this point. I actually want the line connecting this point to the origin. So hang on a second, to 1 comma to f of 1, right? So I also want the point 1 comma f of 1, because that's where I'm calculating the derivative, the slope of a tangent line, right? We want a tangent line over here. And in order to allow our value of a to actually pass 1 here, so we can also go to the right, let's put here -1 to 2 instead, and we can move our point, and look at that, it's going to also go from -1 to 2. It's, of course, it's going to be a little higher here, but you get the idea. All right. So the next thing that I want to do, I want to put on the graph here. Let's stop this. It's kind of annoying when it goes like that forever. So let's do the line that connects these 2 points. So I want the line that connects this one here on the screen with this one here on the screen. So the blue point and the black point. So I want those connected, and I'm going to say y minus minus, let's choose the point. Let's choose our reference point, be this one, 1 comma f of 1 or 2. Y minus f of 1 is equal to the slope, which we don't know yet. I'm going to say m times x minus 1. And I want to choose x. So m will not be a slider, but rather m will be defined here as, and I'm going to choose this point m to be the slope of this, line. So the slope of this line will be fraction, right? The slope will be f of a minus f of 1 divided by a minus 1, right? So there we go. With this thing here, so I found the slope of a line, and then I wrote the equation of a line here. With this thing here, we are in business here. So basically, we can tell what the slope is, and we can also visually see how the line really, as x approaches 1, this line approaches the tangent line. And we will see that that is the thing here. Look at that. Okay, there we go. So at that point, we really are approaching 1, so the tangent line. And as we approach the tangent line, you can see that the slope, I'm going to try to stop it right there close to 1. There we go. Oops. A little closer to 1. Let's move it a little closer. There we go. That's very, very close to 1. And you can see that the slope here gets very close to, you probably guess, very close to 4. All right. So what we're saying here is that the limit of this expression as a gets very close to 1, this limit is going to be 4. And now we're going to calculate that very quickly now, and then we're gonna finish our lesson. And that's what I'm gonna do here. So I'm gonna calculate, folks, f prime of 1, which is the limit as x approaches 1, we said, or yep, so it will be 2x squared minus 2 times, when f of 1 is 2, right, divided by x minus 1, and that's going to be 2 times factor of 2 at the top, 2 times x squared minus 1 over x minus 1, the limit as x approaches 1. I'm just going to carry this and I'll put the limit at the end. 2 times over here at the top, we did this before, x minus 1 times x plus 1, factoring the trinomial, yeah, over x minus 1, cancel these, and that's going to end up being 2 times the quantity x plus 1. All I have to do is to substitute 1 in here. So if I calculate the limit of this guy as x goes to 1, this is going to be, now I'm just going to hurry a little bit here, 2 times 2, and that's going to be 4, which we found graphically as well. So the derivative at 1 turns out to be 4 for this particular function. Now, all right, folks. So I'm just on time, perfectly on time. Thanks for coming to class here. I'm going to stop the recording and I will wait for you to tell me